Today, I'm going to cover 2.1.6. Please, please, please use a pencil for notes and make sure that you have an eraser because we are going to be changing the direction of force vectors. All right, we have two different kinds of forces. There are compression forces and tension forces. So compression is a body being squeezed. If you put your hands palm to palm together in front of you and press on one another as hard as you can, that's compression. Tension, if you think like a chain, a linked chain being pulled from each end, it is in tension when it is snapped tight like that. If you release it, that chain sags and it no longer has any tension on it. Right. Trusses are made of members, gussets, and joints that hold the structure together. All right. Trusses are made stronger by adding triangles to it. They make triangles by adding diagonal members. That way it can't be pushed as easily. You guys should have this drilled into your head, but here's a review of pin and roller joints. Our pin joint is here at the top, okay, triangular. Roller joint down here at the bottom is a circle. Excuse me. All right. For this homework, we are going to make some assumptions. When we solve these truss forces, all of our members are perfectly straight. All of our loads are applied at joints. All the joints are pinned and completely free of friction. Each structural member has no weight. And members can only experience tension or compression forces. Okay, that's just for this homework that we're doing. We're going to make assumptions to make our homework much easier. Now, if we were designing an actual bridge, we definitely know that those beams on bridges weigh a lot. And we know that trucks drive over more than just joints. So the loads are in all different areas of bridges or people walking through buildings. So all the loads aren't just at the joints. If you've ever bought anything from Home Depot, you know that all members are not perfectly straight. And there's friction in everything in life. Okay? All right. We're going to cover statically determinant. In order for something to be statically determinant, the number of joints times 2 is set equal to the number of members plus the number of reaction forces. If those two numbers are equal to each other, we can go ahead and build it. Okay, so J is the number of joints, M is the number of members, and R is the number of reactions. So, joints A, B, C, and D. There are 4 joints here. Now count all the members. Those would be your straight lines. So you have A to B, that's 1. B to C is 2. C to D, 3. D to A, 4. And D to B is 5. Both of these joints are pinned. And remember, a pin has a reaction force in the X and in the Y direction. So there are 4 reactions, 2 Y reactions and 2 X reactions. So 2 times 4, set that equal to 5 times 3, that would be 8. Is that correct? We have 4 and 5 reaction forces. No, we had 4 reaction forces. So we had 9 to 8, which was not statically determinate. We needed to get rid of 1 reaction force to make it work. Okay. 2 times 4 is not equal to 5 plus 4. So if we turn that pin at point C into a roller, we would be golden and we could build that truss or bridge. Just like this image. Ta-da! Buildable. All right. Here is an example of a bridge. There is a roller at one end and a pin at the other. Each dot represents a joint. We're only calculating one side of that bridge. So you can calculate all the members. And this bridge actually exists. It's in New York. This is just a review of the equations we have been over. It's very important to know these equations. So our equilibrium equation is the sum of the moments equals 0. We also want the sum of the forces to equal 0. We have forces in the x direction and in the y direction, so sum of the forces in the x direction needs to equal 0. Sum of the forces in the y direction needs to equal 0. Okay. To solve a truss, use the sum of the moments. So number 1 is draw a free body diagram. We're going to label the forces, the dimensions, and the angles. Okay, and that's the first step. So on your notes right now, there should be a number 1 with a circle around it, and it should say draw free body diagram. Label, comma, forces, comma, dimension, comma, angles. Then you're going to draw number 2 with a circle around it. Set up equation to sum moments. And underneath that, you're going to write, pick a point to rotate about. That's going to be your pivot point. And as a reminder, choose a pin joint. By choosing a pin joint, you have a reaction force in the X and in the Y direction. Okay, it will make your life much easier to choose something that has more reactions. So all of our moments for this example here would be calculated around point A. So now we need to figure out if we are having clockwise or counterclockwise moments. So C and D do cause moments about point A. We need to put those into our equation. Remember, clockwise is negative, so that's going to be our D. D is pulling down, and it's going to cause a clockwise moment around point A. And the moment for point C, that is going to be counterclockwise, which is positive. So now we need to solve for our unknown, and our unknown is the reaction force at point C in the y direction. Okay, We're going to sum our moments about point A. We're going to get into the equation part on this PowerPoint. So remember, D is negative. When you draw your free body diagram, label these. So force D is negative. It's going to be multiplied by 3 feet because it's 3 feet from our pivot point A to point D. We're going to add that to reaction force at point C in the Y direction. That's going to be multiplied by 10 because it is 10 feet from point A that we're pivoting around to point C. We're going to add that 3 plus 7 and get 10. Then the next line here, if you can see my mouse, they substituted the 500 in. Remember, that is negative. It is clockwise. So 500 pounds times 3 feet plus our reaction force at point C in the Y direction times 10 feet. So now we need to get C by itself. So 500 times 3 is 1,500 foot-pounds plus reaction force C in the Y direction times 10. So we'll add 1,500 to both sides. And then we're going to divide by 10. So 1,500 divided by 10 equals 150 pounds. So reaction force at point C in the Y direction is 150 pounds. All right. Now, can we sum our forces? So if we know that we have 500 pounds down and 150 pounds upward, can we figure out what the reaction force at AY is? So I'm gonna go right here. We have negative 500 pounds, right? That's going downward. We add that 150 pounds and we're gonna figure out what our AY is. So what's left is negative 350 pounds. That means that our AY has to be 350 pounds in a positive direction in order for those beams to be in equilibrium. 500 down, 500 up. Now we need to do the forces in the X direction. The only force we have in the X direction is reaction force A in the X direction. So if we want the sum of our forces in the X direction to equal 0, they're 0. Reaction force A in the X direction equals 0. And that was because we don't have any other X forces. All right, this is called the method of the joints. So we have to perform the method of the joints on every joint in the truss. So write this down, method of the joints. Step 1 is to select a joint. Step 2 is to draw a free body diagram for just that joint. So here is an example of a free body diagram just for joint B. So we have B and we have the members that are coming from point B. We initially start this drawing all the arrows away from that joint. So write down, draw all the arrows away from that joint capitalize away, highlight it, circle it, underline it, make it bold. Then the next step is we're going to assume all the members are in tension. Okay? You should choose the joint you know the most about. I don't know the internal member forces for AD, BD, or CD. So D is not a good joint for me to choose. I do know RCY, but I don't know the internal member forces of BC or DC. So that's a couple unknowns to solve for. I do know RAX and RAY. I don't know the internal forces of AB or AD, but I think I can pick joint A. So we're going to solve for the angle at point A. We're going to use trig. Remember, this is arctan. So on your calculator, you're going to have to hit second and then tangent. There's a lot of graphing calculators online that you can use. There's apps that you can download on your phone, but most of the good ones you have to pay for. So here's our angle at point A, 53.13 degrees. All right, let's see if we can find our other angles. Solve for angle at joint C using trig. Remember this little negative sign here? That's your arctan. So the angle at joint C is 29.745 degrees. I am not doing these myself. I'm just using the PowerPoint, so your calculations may be more accurate than the PowerPoint has. Okay, we are going to draw a free body diagram of all the joints. So we don't make them connected. They're all their own free body diagram. You can keep them in the orientation that they originally were in, but make sure that you leave space to be able to write around them. Or you can just do joint A at the top of your page, B is the next one down, then C, then D, whatever works for you. I prefer to keep them in the orientation that they're in the truss so that I can keep track of which one's in compression and tension and when I need to flip the forces. So we're going to choose the joint that has the least number of unknowns. Reaction forces at joints A and C are both good choices to begin our calculations. So here are the things that we know. We calculated the two forces that are in red. We were given the force in blue. So we're going to choose A. All right. We're going to find the sum of the forces in the Y. we're going to set our equation equal to 0 because we don't want our bridge to fall down. Reaction force A at point A in the y direction is obviously a vertical arrow. Now there's a component of AB that is up down. So you can take the hypotenuse of AB times the sine of 53. Okay, make sure you're setting equal to 0 and solve for our unknown, which is AB. All right, our number came out negative, which means that member is in compression, and we originally guessed tension. We're going to draw all these arrows in tension first, remember. So we're going to go back to our free body diagram, and we're going to change the arrow to go toward the joint. So like this. See? Arrows that go toward the joint are in compression, away from the joint are in tension. So now you know to go to your free body diagram for point B and change the direction of the arrow. So go back there now. That's why I said to do your notes in pencil. And we know AB is in compression. Okay. All right. Now go find the sum of the forces in the X. Remember, there's a component of AB in the X direction. So find AD. AD is positive. Let's see. It's in tension. We already solved for AB. Just doing algebra mixed with a little trig. Okay, we're going to keep this one in tension. Now we're going to do joint C and sum the Y. So we have all the forces in the Y direction, reaction force at point C in the Y direction, and then a component of BC in the Y direction. It's 150 pounds plus our component, and our component is BC sine of 29.745. Okay, it came out negative. Remember, negative means compression. We need to go change our free body diagram. So we'll go back over here, pay attention to B and C. You don't have to take your arrows and put them over here. You can just change them right here to point in this direction. We will know if it's pointing toward the joint that it is in compression, it's negative. right, now at joint C, we need to do our forces in the x direction. Already solved for BC, and now we need CD. Get CD by itself. It is positive, so it is in tension. You don't have to change any arrows. Now we need to do joint D. First, we're going to sum the forces in the y direction. Plug in our known values, because they're 500 pounds, which makes it really easy. So if we have negative 500 pounds, BD has to be a positive 500 pounds. It's in tension. Okay, now your whole truss is solved. So why do you have to learn this? Well, if we were in class, you would be building a balsa wood bridge. And then we would see how much force it takes to break that bridge with our force sensors. We'd work really hard to build them, and then we're gonna crush them.